Okay, so morning again. We are continuing this morning with nuclear physics, seeing how much we can wrap up today. Right? If we finish up today, we finish up today. If not, we just have a wee bit more left to do at the end. So just to recall where we are or what we're doing right now, when we talk about atomic physics and nuclear physics, mass and energy are interchangeable topics, as we can use one topic to represent another one. Okay, so not topic here, not just topic, we're talking about mass and energy relate to each other, as in anytime energy is emitted or energy um, is lost or transferred into a next form, it reflects itself as a loss in mass. And we call this the lost energy or the binding energy of a nucleus. Binding energy is the energy required to bind your nucleus together. And as we did see last day, the total mass of your nucleus is less than the mass of the individual particles. And of course, we are in opposite world. That makes no sense. How can I break a plate and then I take up all the particles of the plate, and that all those particles put together is heavier than the original plate? Right? What happens when it comes to the nucleus? Energy and mass are related to each other, such that when we lose energy, we also lose mass. Okay, so that's called our binding energy or mass defect. Mass defect is just the difference in mass from your nuclides to your nucleus. And when you want to work out binding energy, as if you want to go through here again, there are two ways to work it out. You can use mass defect by c squared, which is the less likely term we use at this level because we talk about such small numbers. We will use unified atomic masses instead because that's the number we're working with. So if you want to have binding energy in mega electron volts, we did do this last day, it's 931 by your mass defect in terms of unified atomic masses, or U. So that's our equation, right? Our binding energy is equal to 931 U. U is just your mass defect, so it's going to be the mass of your total nuclides, total amount of nuclides, minus the mass of your nucleus. So just multiply two numbers by each other. Or if you don't have the 931, E equal mc squared applies, where m is your mass defect, c squared is your speed of light squared. So let's continue reading. This is where we had reached last day. Please note that the binding energy of the nucleus is the energy required to break the nucleus into protons and neutrons. So this is the binding energy of a nucleus. The binding energy of an atom is the energy required to break up the atom into electrons, protons, and neutrons. But since the energy required to move an electron is considerably less, it's so much less, it's basically considered to be zero compared to the rest of the atom, we can take or we can make the assumption that binding energy of a nucleus is equal to the binding energy of an atom. Why do we say that? Because electrons, we could move an electron with friction. Or we could be bad enough to say we can blow on a metal hard enough. We can take a charged wind and pass it over metal or pass it over material, and we could remove an electron. You can't do that with protons and neutrons. You need really big forces, really big energies to move your protons and neutrons. So that's why the binding energy of atom and nucleus are essentially the same thing. So let's take an example here. We want to look at the binding energy of helium. We have here helium has a mass, which is the same diagram we had above, right? The total mass of a helium atom, 2 protons, 2 neutrons. Let's go in a little bit closer. Hope you have your calculators around. I don't even know where my calculator is, but all right. So we have the mass of helium, 2 protons, 2 neutrons, 2 electrons. And if you want to get the total mass of your particles, Please note they're never going to ask you to learn the masses of your particles. They will give you that. But what you should know, even though that's written in your Rubik sheet, what U is. Remember, U is unified atomic mass, and we have that as 1/12 the mass of a C12 atom. Don't worry about learning that number either because it's also in your Rubik sheet. Just know what it means and know when to use it. So we have here 2 by your mass of your proton, 2 by the mass of your neutrons in terms of unified atomic masses, and 2 times the mass of your electrons in terms of unified atomic masses. So when you add them up, you see why it's really much easier to work with U, because you don't have all those sort of decimal places and small numbers to work with, because human error is a thing that we all encounter. So the mass of a helium atom will be 4.0026 unified atomic masses. The mass defect, now if you wanted to get the mass defect, what you had to go and do is to get the actual mass of your particles minus the mass of your helium. So this is written in your periodic tables. If you all have ever looked at your periodic tables, you're going to see that they have these precise numbers written in them. Everybody ever notice that?
Yeah.
All right, if you take a look at a good periodic table, not a periodic table you have used in Form 3, but one that you all have like in your Form 6 textbooks, you're going to realize that they don't have the atomic masses for 7, 9. It's usually a number with a bunch of decimal places. So that's the actual number of the atomic mass of the atom and the element. Well, the atom in that element. So mass defect is 4.033 minus 4.022 to give you 0.304 unified atomic masses. So this is the mass defect of your helium atom, which is the mass of the particles minus the mass of the actual atom. And if I wanted to find the binding energy in terms of mega electron volts, right, remember binding energy is just going to be your mass defect by 933. So it's going to be 933 multiplied by 0.304, 0.0304. Now, if you wanted to work this out in terms of joules, it's just going to be mc squared. So it's going to be 0.0304. Now you're going to have to multiply the value of u, right? Because remember, value u represents a small number, and then you're going to multiply it by c squared, and this is going to be your number in terms of joules. This is mega electron volts, and this one is in joules. So please know how to use both versions, no matter what. So carrying on. When the binding energy of a nucleus is divided by its mass and by its mass number, the binding energy per nucleon is obtained. All right, so per nucleon being for each element, there is their own specific number allocated to them. This is a useful measure of the stability of the nucleus. So remember we said there was no way we could just look at an atom and determine how stable it is, but there's a way we can calculate how stable our atom is by looking at our binding energies per nucleon. So what we have here, if you look down, we have a graph of your mass number of each element, and then you have your binding energy per nucleon in mega electron volts. So all you have to do is just get your binding energy per nucleon. How do you do that? You find the mass of the particles minus the mass of your atom. You multiply by 931 and you get your number in terms of mega electron volts. And they've come up with a really nice table. And if you look here, we start, the lowest one is obviously going to be hydrogen, right? And then that's just hydrogen, an isotope of hydrogen, because hydrogen regularly is H11. So this will be an isotope of hydrogen. So the lowest one here is hydrogen and helium. And look here, we have two different nuclides of helium. We have helium 3,2, and then we go up to regular helium, helium 4,2. Look at the big energy jump, the big, big, big jump to go from one isotope to the next. And then we dip down to something that's a little more stable. All right, then we go up. So it kind of zigzags, it goes up and down for a little while. We have oxygen, then it goes pretty much, it goes up and slightly and curves down. The element at the top here, right? Iron, why is my door keep knocking? Iron 56 is the highest element on this table. There is no other element that we know of so far. All right. Well, basically, we know all of these elements in between. All right. There's no element that reaches higher on this table, and how high this element is tells us about the most stable nuclei that there is. And the most stable nuclei that exists is iron 56. All right, most stable. It doesn't go through any sort of atomic degradation. It doesn't go through that. So that's why you don't hear about radioactive iron. I've never heard of radioactive iron. Never. All right, you can get isotopes of iron, but iron 56 is the most stable atom we have. All right, just to tell you that when it becomes stable, when stars start to create iron in their core due to fusion, the star starts to break down, it starts to die. That's the instant, that's the death stroke of a star. The instant it starts to make iron, game over. That star is now going to, it's reached its peak, it's now in the dying phase. It's going to now start to die out because it's gotten as stable as it has gotten. It's not going to have any more fusion going on, right? And it's going to stop there. And what happens as the curve goes down, we get our different set of elements. So here we have uranium 23892, right? There are more elements. Obviously, there are more elements in there because we have the rest of the radioactive group to put in there. But this is what you all are supposed to know. This is the group that we get in exams, right? Where we look straight up to uranium 238. You don't usually get more elements than this in your table. If they give you anything, they for sure will start you off at the bottom with hydrogen, your 2 helium isotopes. They're definitely going to speak about iron because iron is the most stable atom that exists. And then they're going to just give you random ones that go down. So you have to be able to know to describe the curve. Why the curve is the way it is, it just explains the stability of the element. And you can see here, obviously, where an element is in the periodic table doesn't tell us how stable it is because uranium, it's a big atom. Of course, it's less stable, right? And you can have atoms right before and right after iron tend to be a lot more stable because you don't hear about isotopes about them that are unstable atoms that readily undergo radioactive decay and whatnot. So it's a good way of determining how stable your atom is regarding radioactivity and decay and that sort of nuclear energy. All right, we're not talking about rusting because nobody likes to rust like iron. Right? Anything, right? Rusting is a chemical process. Nuclear energy is an atomic process. Two very, very different things. One is a chemical reaction. This is more fundamental and deeper down. All right? So the highest element on the curve is iron 56, and it's one of the most stable elements that exist. Hence why we have a lot of iron in our planet, on our planet, in our planet. All right, when we get things crashing into Earth, they're usually made up of iron. Iron is a very, very abundant element, not just on Earth, but in the universe. So how do we use this curve? What is the purpose of this curve? This curve tells us where fusion and fission happens, which is kind of important to know. You want to know who is going to have fusion and who is going to have fission. All right, so nuclides of intermediate mass numbers have the greatest binding energy per nucleon, intermediate being in the middle of the table if you look in the periodic table, and therefore energy is released when two light nuclides are fused to produce a heavier one. All right, so anything before iron, any element that exists before iron undergoes nuclear fusion. All right, this is how the table works, right? Anything before iron, you realize that any element that happens before iron will undergo some sort of nuclear fusion, right? They readily combine those two to create fusion. And what happens? We get energy by splitting anything after iron we use for nuclear fission. So this is how we use them. If you want to fuse two atoms together, we use our elements before iron. And if you want to split atoms to create nuclear energy and whatnot, we use anything after iron. All right. So let's note where we have water on the curve, where we use what material. Anything before iron usually comes about by nuclear fusion. Anything that happens after iron usually undergoes nuclear fission. Nuclear fission. Energy is released by this process because the average binding energy per nucleon in the fission products is greater than the parent. So let's read that again. Nuclear fission. Energy is released in this process because the binding energy per nucleon in the fission products are greater than the parent. So what we have here, as I said, this is our big equation. This is our big nuclear reactor equation. Not nuclear, this is our nuclear bomb equation. All right, so we have uranium-235-92. We went through this where it's hit by a high-speed neutron. It absorbs that high-speed neutron, it destabilizes and then explodes. And it explodes into, now it doesn't always explode into barium and krypton, but in this case, we have barium and krypton with 3 extra neutrons that go on to interact with more uranium-235s to create a chain reaction. We'll see that just now. Oops, I think it wanted to be seen right now. The energy released from a single uranium atom is 300 mega electron volts. So it's a lot of energy contained in one single uranium atom, as in the one explosion of that uranium-235 to give you the barium and krypton is 300 mega electron volts. 80% of this goes into providing kinetic energy for the fragments, all fragments being barium, krypton, and most of them into your neutrons, because neutrons have the smallest mass, so they're going to move the fastest. 10% goes to heat, and it's this heat that we use for our nuclear power plants, just the 10%. And 10% goes to neutrons and gamma rays. So when it comes to uranium-235, you do have gamma rays produced as one of the byproducts of the reaction. The neutrons go on to form a chain reaction when they bombard other uranium-235. Nuclear reactors utilize controlled fission reactions. Atomic bombs make use of an uncontrolled fission. This is why weapons were developed before reactors, because we had no idea. We were just there playing. Let's take this and let's hit it with something else, and we get a big boom. Right? Then they realize, if you use small amounts, we can control. We know how much energy is emitted by one uranium atom, so we can just scale it up to get the amount of energy that we require and that we can use. When we have a massive amount of energy output, there's no way we can't control it. There's no way we can harness it because it's too much energy to take use of. So here we just we'll go through how, unfortunately, we cannot go through how nuclear reactors work, but we'll see where we reach. So that's to tell you, all right, I have here just out of academic curiosity, because I was a little curious to see where these actually lie, because we have uranium-235, and depending on the speed of the neutron, that uranium-235 can be destabilized in a numerous set of ways, right, when it's hit by that uranium atom. So we can get strontium and neon, bromine and whatever that I don't know what La is, rubidium, cesium, tellurium, zircon, barium, krypton. So you can see there's not just one reaction with uranium-235 and a neutron. The one that we learn is this one here that gives us the barium and krypton. But depending on the speed of your neutron, obviously the speed of the neutron is going to make a difference, because when we take a high-speed neutron and fire it into our uranium, we put more energy into that uranium, right? And if more energy goes into it, that means they're going to explode. Well, it really does explode into different size fragments. Think about it the same way if you drop your plate. If you drop your plate like from elbow height, you're sitting down and it just drops. If you're lucky, it might just crack when it hits the ground and you'll just get a few little splinters. But if you drop a plate from upstairs and to the ground, adding more energy, you're going to get far more different set of results. So the same thing happens here, right? And if you look here, we actually do get different amount of energy released by different types of reactions. But the reaction that we use in the nuclear power plants, 235 to give us barium and krypton. So they know the speed of the neutron that they're firing into the uranium. So it's not like, it's completely random. They know exactly what they're working with, and they know how much uranium they have. They know what compound uranium is in. They know what speed the neutron is being fired in it. So they know exactly how much energy they are going to get. It's not just random. Ibrahim coming in. All right. So this is your barium and krypton. If you wanted a nice, good visualization, this is what happens when you fire that neutron into your uranium. It becomes uranium-236. It begins to destabilize. It's now an unstable nucleus because that 236 is just too much. Uranium is good at 235, but 236, 236 was just too much. And it destabilizes, explodes, and the excess neutrons go on to hit more uranium, forming your chain reaction. All right, so this is how you end up getting your chain reaction. Right, one goes on to hit more and more and more, and it takes place in a matter of milliseconds, not milliseconds, microseconds. Each hit that happens very, very, very quickly, or not even nanoseconds probably. All right, so nuclear fission reactions. Oh, excuse me. Right, so here's just a next diagram of, or not next diagram, but just the values they have for different type of nuclear fission reactors, because we don't only just use uranium. Sometimes you use uranium, sometimes plutonium. All right, so it's just me being a little extra finding, more information, because we only hear about one and there's far more than just one. So we have uranium-233. They use uranium-233. Now that's a synthetic uranium. So that's one that they actually made by doing some sort of bombardment with neutrons and whatnot. Uranium-235 is what they take out of the earth. We have plutonium-239. Plutonium-239 is a synthetic plutonium. How do we get synthetic? We bombard them with neutrons, or we create an isotope. We can create isotopes, right? If we can split an atom, we could create isotopes. All right, and here we have how much energy we get, what we get from them. All right, so uranium-233 gives us strontium and neon with, you can see how much energy is generated from each reaction. So it's not much difference. Some nuclear power plants have their own preference to what they want, and others, have likewise. So they make their power plants suitable, or they use a suitable amount of material for their power plants. Nuclear fusion. The union of two light nuclei to form a heavy nuclide can also lead to a transfer of mass and consequent liberation of energy. Such a reaction has been achieved in the hydrogen bomb. If you want to read up about the hydrogen bomb, go ahead and read up about it. And is the principal source of the sun's energy. We know we get energy from the sun from nuclear fusion. Jabari, the nuclear fusion and fission, remember that, right?
Of course. How could I forget?
Mm-hmm. Right? So a reaction with heavy deuterium or deuterium yields 3.3 mega electron volts per fusion. So what we're going to get when we take two hydrogen, two deuterium, fuse them together, we're going to get an isotope of helium, right? So helium 3 2 and an extra neutron. So by comparison, one uranium 235 atom gives us 300 mega electron volts of energy versus one hydrogen fusion gives us 3.3. One is much, much, much smaller. But this seems small, but per mass unit, the yield is far greater. Jared, why is your camera on? Man lie down in bed watching class. Y'all, that's the life, yes. Right? So what happens because uranium is so much heavier, right? Uranium is quite a bit heavier than hydrogen. If you look at it, uranium is 235 times heavier. No, 92 times heavier. 92 by 3.3. It's going to give us more than 200, right? If you were to do the actual maths and see per yield per mass of product, right? If one uranium gives us 200 mega electron volts, and uranium is essentially 92 times heavier than hydrogen. 92 by 3.3 will give you 6 something. Somebody do that multiplication. I have people. All right, 3.3 by 100. You're going to get about 250, yeah, nearly 300 mega electron volts in,
Is it 92 by 3.3, right?
yeah, how much you getting?
303.6.
303.6.
300 and,
3.6.
you see I was close with the maths, you know? Right? 303. So look at this. If you take the same product for product, same mass of uranium compared to the same mass of hydrogen, you're going to get more energy from hydrogen. It's just because hydrogen is far lighter than uranium. It looks like less, but mass for mass, kilogram for kilogram, fusion generates more energy. Fusion of two deuterium will only occur if they overcome their mutual electrostatic repulsion. And that is the big problem when it comes to dealing with fusion, why we have not generated fusion reactors as yet, because you need a lot of energy to force two hydrogen atoms together. A lot of energy. In fission, we just fire one into the next. We heat up some neutrons and fire it into something. That's not such a big energy. But fusion requires a lot of energy just to happen. So if fusion occurs, enough energy is released to keep the reaction going. This reaction is called thermonuclear fusion. Why we call it thermonuclear fusion? Of course, heat is generated, and once you have your first fusion reaction happening, it creates enough energy to essentially fuel the other atoms of to fuel the other fusion reaction. So this is what they need. This is something called ignition. For stars, you need to have ignition. When it reaches a particular temperature and pressure, a star will ignite, basically like turning on a switch. It will ignite, and then nuclear fusion starts to happen. So that's the thing of how stars build. They collect materials, form a protostar, and that material keeps collapsing and collapsing on itself until it gets really, really small. And when it collapses, well, really small in terms of the cloud that formed it. All right, it's still really big to us, but when it gets small enough and dense enough, it has enough heat in the middle to cause those fusion reactions to happen. And once you have the first fusion reaction, just the first one, enough energy is there to cause a chain reaction to make the next ones happen. So it basically ignites. So stars have an ignition switch or an ignition process. Pretty cool that, and you need a specific term to reach. And once it starts, like a switch, and it goes off and it just ignites and explodes and starts going and doing what it has to do. Temperatures of 10 to the 8 or 10 to the 9 Kelvin are required for this process. So this is the problem with thermal nuclear fusion or nuclear fusion. It requires a lot of energy, a lot of heat for it to happen. Recent experiments using deuterium and tritium plasmas confined in a high magnetic field has produced yields of 17.6 mega electron volts per fusion, which, y'all, that is more energy. Let's look at this, right? This one at the top here was only 3.3. This one here is yielding 17.6. And remember, if you multiply that 17.6 by 92, that is far more energy than a single uranium reaction. All right, anybody who has a calculator, give me that number fast.
1619.
1619 mega electron volts.
0.2.
The point we're making a difference now. Once you start reaching thousands and stuff, those decimals don't play much of a role. So look at the difference. When we did experiments with deuterium and tritium plasmas, right, we end up getting 16,000 mega electron volts just by combining, under the right conditions, two hydrogen atoms, which is, that's 8 times the amount of energy generated by a single uranium atom bombardment. So this is how they know that nuclear fusion creates more energy. It does create more energy, but the thing is about you running nuclear fusion, you have to spend a lot of energy, which means a lot of money to make that happen. All right? How do we make nuclear fusion? How do we conduct nuclear fusion in planet? No, we do not have the stars as Dr. Octavius had tried to do. No little stars ignited in a big little containment unit. The way how we create nuclear energy on Earth is very different. We use something called a tokamak. All right, this is called a tokamak. A tokamak basically has very strong magnetic fields generated on both sides. So we have really strong magnetic fields. And to run very strong magnetic fields, we need very high currents, because how do we make these magnetic fields? We use an electromagnet, right? And we know when we talk about using electromagnets, we need to use a high number, or high value, or high level of electricity, very high currents, to generate very high magnetic flux densities. So they use a lot of current to get a very, very, very strong magnetic field. And then inside here, they have plasma that they heat up. And how they heat this up, they get it faster and faster. They just rotate it so it gets really, really fast. And by running this material very fast, it gets very, very hot. And the material inside of that coil ends up undergoing nuclear fusion. And the heat is used, the heat generated, they use for just running turbines and other stuff. But this takes a lot of energy. I think I have a picture down. I didn't put one down. I'll get one down for you all. All right, so here are just some examples of the various, now all the tokamaks on the planet. There are quite a few countries that have tokamaks running for experimental purposes, because this is only producing hydrogen, helium, lithium. None of those particles are going to be radioactive. So there's no radioactive or hazardous byproducts of nuclear fusion. All you're going to get is helium and then steam. So this is why a lot of countries that can afford it, because it takes quite a bit of energy, quite a bit of money to run these things, right? So a few countries that can afford it have been experimenting to see if they can get a economical process of running nuclear fusion. Because if you could get an economical process for nuclear fusion, our Our energy problems are done, are over, because the same amount of energy that they require to run the tokamaks, they're going to have to use some of that energy generated by the tokamak to run it and then issue out the rest. So here we have the various forms, right? Remember, there's more than one way to do something. And here we have deuterium and tritium to give you helium-4, deuterium and deuterium to give you helium-3, two different deuteriums, right? Depending on how much you end up giving off. Protinium, you all can go and look up what that is, right? So we have different things being processed and being formed. I think the biggest news right now, just recently this year, China had fired up their tokamak, right? And it ran successfully for a few seconds, which is really, really, really nearly getting their stage. For it to run a few seconds, that was us making a big step forward in using um, nuclear energy in the future. Because think about it, this only produces helium or hydrogen isotopes and steam. And once you have enough electricity to run it, you're going to run it. So oil is nearly done. Gas has to go. Coal has to go. Right? We know wind can only be used in certain places that can support the wind farms. Trinidad, even though we have Toco area and stuff, they did go and test out a few areas in Trinidad, and we did not have the sustained amount of wind to run wind farms. So that was checked a long time ago. So I know a lot of people ask why we don't run wind farms. But like right now, it's kind of nothing outside. They can't have those big turbines just sitting down doing nothing. They have to be they need a consistent amount of wind basically all the time, which is what consistent means, right? To keep those farms running. Solar works, but solar doesn't give you the big, huge power draw that you need for industry, right? And if you do need, you need a large land space to get a solar wind farm. There are big solar reactor kind of farms where they take a whole bunch of solar panels and they use it to generate a lot of energy. You all can look that up if you want, right? It's huge, it's massive. It takes up about a couple acres of land where they have solar panels all lined up in a circle kind of way to generate all the energy. Wave, you all know wave energy is only available where there's wave energy. Hydrothermal, only, and that has serious environmental impacts, right? So, your nuclear energy is where it's going to be. If we have to send people out to Mars, they're going to have to use nuclear energy in some form or fashion. All right, they can't use the sun because dust storms and all that stuff. All right, so radioactivity, this is where you all are going to need to do some reading. All right, so please read this up. So we have revision of Form 5, radioactivity. So you want to look at, and you're all going to listen carefully what we need to look at if you're writing down notes. I hope you all write down notes when I'm giving class. Your three particles, the overview of those particles. But what is different in this case for CAPE, you need to know how to detect those three particles using cloud chambers and yeah, cloud chambers. Right, I have a video somewhere. I'll have to find it and send it to you all because when I was at CERN, I did actually see a cloud chamber, and you could see how each particle was moving through the cloud chamber. Right, it's really, really, it's not something where you just see a little spark. You actually do see the trails of the alpha, beta, and neutrinos and stuff passing through your cloud chamber. So look how to determine the track of your alpha, beta, and gamma particles using and gamma rays using cloud chambers, how magnetic fields affect them, and how electric fields affect them, because one is different to the next. One particle is attracted to a magnetic field and then repelled by it, and then another particle is attracted to an electric field and the other particle will be repelled by it. So read up how to determine them, how to see them using cloud chambers, and how how electric and magnetic fields affect your radioactive particles. Read up on safety precautions and stuff. You all should read that up, or you should know how to do that, meaning to read it up. Read up on the use of on reactive materials in industry and medical fields. I'm creating a little document for my Form 5, so I'll just make a little bigger one for you all so you that can just, that's just a reading topic. We're not here to do reading. You do that in English class or communication class. I'll save all day from that. All right, then we're going to go on to the K law. Do we have enough time to do the K law? Yeah, man, we have enough time. We can just start up and then we'll stop and run full into the next day. So the K law, which is, when will I see you all again? Thursday, Wednesday, I'll see you all again. So we'll finish up on Wednesday. So radioactive decay is completely haphazard and random in nature. We know this, right? As in, when we talk about half-life, it's an average value, but it's so average or it's so consistent, we do use it as a characteristic property of a material, but it's still random. It is still haphazard. It's not like a uranium atom is going to be giving out 2 beta particles every single second, every second that it goes. No, right? It has to take an average of some values and you get a pretty consistent number with the averages. So please note that radioactive decay is still random in nature. Since there is a large number of active nuclei in a given amount of radioactive material, statistical analysis is applied to determine your relationship. So because it's haphazard, meaning this very second a sample could give off 500 disintegrations, next second they could give off 395, next second it could give off 700. So they use statistics to level off that up and down value to give us an average number. So this is where we go a little more. We assume that the rate of disintegration of a given nuclide at any time is directly proportional to the number of nuclei n of the nuclide present. So meaning, let's do some maths here. Negative, anytime we have negative in any sort of equation, whether it be calculus or whether it be exponential, that means that we are decreasing. We have a decreasing relationship. All right, we're not going to go through the maths because it's not required. You just need to know the equation. All right, so those who know how to use the maths, you all can go ahead and use the equation, but let's just look at it. What they say here, the rate of decay, dN dt, means how much active nuclei changes with time. That is what this means. N tells us the amount of nucleides we have at any given time, and dN dt means change. So the change in the number of nucleides over the change in time is directly proportional to the number of nucleides that we have. You're going to be like, what? Let's see how and why this works with. Let's just think about it. If I have a sample, right, and just think about it in terms of pressure. If you want to talk about a classical term that's really, really similar, pressure works exactly the same way. You all know as pressure decreases, right? You all remember this experiment that you did in Form 5, or this topic we did in Form 5 and probably Form 6. When we have a large pressure, you're going to get a lot more water coming out of a container if it has a hole. And when you have a small pressure or a small amount of liquid, it's going to go less. Same thing here. The more nucleides we have is going to have a larger rate of disintegration, which means, well, yeah, that makes sense. If I have 10 billion nucleides now, after a certain given time, I'm only going to have like a billion or 500 million. And that's going to be less or smaller rate of disintegration because as time passes, more and more of my nucleides are going to degrade and we're going to have less of them available. All right, so the negative sign here, that's reading. The negative sign, where's my pen? Did I stick my pen? No. All right, negative sign here indicates there's a decrease in activity. The radioactive decay equation lambda gives us the equation of minus dN dt is equal to lambda n. Lambda being your decay constant. All right, so lambda n is the decay constant, n is your number of active nuclei, and dN dt is the rate of disintegration. We don't need to go through this. Math students, you all can go through it. It's really simple. All right, But this is how we end up with the equation when we are talking about decay and radioactive decay. The rate at which your nuclides disintegrate is mathematically expressed in the equation of n is equal to n naught e to the minus lambda t. Oh, jeez. Right? So n is equal to n naught e to the minus lambda t, where n is your number of nuclides, right? Number of nuclides at any given time. N naught is equal to your initial number of nuclides. Hold on. School is messaging me. All right, so N naught is your initial number of nuclides, E being natural logs E, lambda is your decay constant, and T is your time at any given time. So what this tells us, the number of nuclides we have at any given time, so this is N at T, right, is equal to N naught, which is the number of nuclides, initial nuclides that you had, E to the minus lambda by the time that you are looking at. So if I wanted to find out, suppose I had again 10 million active nuclei at time 0, and I wanted to work out how many nuclei I have at say 10 days or 20 days. You could work it out, right? Convert it to seconds and whatnot, and you can work out how much you have. So you're going to try this and see. It's a really easy equation to use. And then we'll stop there because I need to discuss something with you all. Oh, good grief, leave me alone. All right, so I just want to discuss with you all what we have coming up. You all they did release the exam topics. All right, let me just save this. All right, pull you all across. All right, and if I pull up my exam topics, the document that they did send was correct. In truth, is just somebody jumped the gun. And of course, somebody's always jumped the gun, doing what they're not supposed to do. All right. And if you look at our topics for paper 2, I'm looking for it. Moderation. Okay. All right. So for moderation, we have, if you all go through the table, it has electrical fields, electrical quantities, electrical circuits, and capacitors. I am pretty much guessing that is question 1. All right, because we have 3 questions, one for module 1, one for 2, one for 3. So question 1 is going to be electrical quantities, electrical circuits. My guess, y'all, we're going to make a guessing game next day what those are, but quantities being, they're going to ask you for some definitions. Then they're going to give you a circuit calculation, all right? And then they're going to give you a capacitor calculation, all right? Next thing they put up, they have an entire topic for operational amplifiers. So that's going to be our question 2. Everything in operational amplifiers. That's fine. We can make an entire question 2 on operational amplifiers. So we're going to do some questions, well, some more questions on them. So don't doubt that they don't give you a whole bunch of definitions first, right? They're going to have to derive a gain equation, right? And then they're going to probably, for sure, they'll give you an inverted and a non-inverted. So we will try to do some spotting later on, but you all know I'm terrible at spotting questions. But here, at least we could revise the whole thing upside down, inside out. And our module 3 question is particulate nature of electromagnetic radiation and radioactivity, which is Planck's constant, or it could be Millikan oil drop. All right, either one of those. And radioactivity. Radioactivity will be this whole topic of looking at radioactive particles, decay law, and radioactive half-life and whatnot. So that's a nice whole question there. So next day, we can start looking out for questions. So we'll definitely finish up the syllabus on Wednesday. And from there, we will be doing, why my shoulder disappear? Yeah, shoulder disappear. All right. Okay. Next day, we will finish up the syllabus and we're going to work out, since we've had to readjust moderation and whatnot. I don't think we're going to miss too many classes now because I think my quarantine runs till next week, Friday. So I ain't going nowhere. All right. And we'll work out some tutorial sessions from there. All right. I've already worked out our tutorial sessions, but I have to readjust it now. We don't need to do so much magnetism again. Don't need to do so much logic gates again. Please note these topics are only for paper 2. Paper 1 could still have everything, but since you all are the first exam, now we try to study quickly and sufficiently and enough. All right, so I will end the recording there, and if anybody has any questions, you will ask. All right, so those watching the recording, bye bye.